In the video on sp3 hybridized orbitals, we went in pretty good detail about how a methane molecule looks, but just as a bit of a review, it's a tetrahedral shape. You have a carbon in the middle, and then you would have a hydrogen. You can imagine I'm drawing it like this because this hydrogen is poking out of the page. Then maybe you have another hydrogen that's in the page. You have one above the carbon, and then you have one that's behind the page. So you can imagine it's like a tripod. It's like a tripod with a pole sticking out of the top of the tripod. Or if you were to imagine the shape another way, if you were to connect the hydrogens, you would have a four-sided pyramid with a triangle as each of the sides. So it would look something like this. It would look something like, trying my best to draw, the pyramid would look something like this if you could see through it. So this would be one side. Another side would be over here, and then the back side would be over here, and then the fourth side is actually the side that's transparent out front. So the fourth side would be the actual kind of thing that we're looking through when we look at this pyramid. It would be this front side right over here. So you could imagine it different ways. This was the case with methane. Now let's extend this into a slightly more complex molecule, and that's ethane. So the way we've been drawing it so far, I guess the simplest way to draw ethane is just like that. By implication, this is ethane. By implication, you have a carbon there and a carbon there, and they'll each have 3 hydrogens bonded to it, and we've drawn it something like this. 3 hydrogens bonded to each of these guys. But now we know that carbon has these sp3 hybridized orbitals that it likes to form more of a tetrahedral shape when it bonds. So an ethane molecule would actually look more like this. Let me draw the carbons. So I'll do the carbons in orange. So if that's the carbon and that's the carbon. So you can imagine you have a carbon molecule here. I'll draw it as this little circle. And then if we have some perspective, so the carbon-carbon bond is going to look like that. And then you have another carbon molecule right over there. So that's that bond over here. And we want both the carbons, all of their bonds, to be kind of in a tetrahedral shape. So then you can imagine this bond over here going like this. This bond going like that. And you have your hydrogen at the end. Let's make the green circles the hydrogens. So you have that hydrogen, and then, or actually just the circles, we'll call them hydrogen. And then you can imagine this one, maybe it's coming out of the page a little bit. That is that hydrogen. That is that hydrogen. Let me label the hydrogens actually. I'm doing it all in different colors so you can see what I'm talking about. And then this hydrogen is going right below it, maybe pointed back a little bit. So that hydrogen is right over there. So you can see this carbon, its bonds have a tetrahedral shape. Or if you just looked at this part of it, these would be the base of the tripod, and this would be the thing sticking up. Now for this carbon, it'd be a very similar idea. This hydrogen right here might be sticking down like this. And I'll stop switching colors soon enough. It takes a lot of time. That hydrogen over there, it's pointing out in that direction, like that. And then you would have, let's see, what colors do I have left? Well, I'll just do yellow. That hydrogen right there, maybe it's pointing out like that. So this is a possible configuration for ethane. And the way that I've drawn this right now, and you can actually have a model that has this, where you have little wooden sticks with balls in this, that balls to represent the actual atoms. This is called a ball and stick model. Ball and stick model. And this is a ball and stick model for ethane. Now, a simpler way we could have drawn this, and this is called a horseshoe projection, or actually no, it's a sawhorse projection. I always say horseshoe. A sawhorse projection. It would look like this. This exact same configuration of ethane in a sawhorse projection. And you know what a sawhorse looks like. A sawhorse. Well, it looks like what I'm about to draw. It looks like this. So you could, well, I could draw it exactly the way I drew it here. So you have the carbon, carbon, and then you have the hydrogen, hydrogen, hydrogen. And then you have the way I've drawn it, well, the way I've drawn it up here is more like this. Just so we see the parallel, and then we can rotate things around. The way I drew it up here, you have a hydrogen, hydrogen, and hydrogen. And then over here you have a hydrogen, hydrogen, and hydrogen. This is a sawhorse sawhorse projection. Now, either way you depict it, I mean, these are really the same way. This is kind of just like the lazier way of doing it on some level. You're not drawing all of these circles and all of that. And you're putting a little less care into actually showing the angle, how things are angled away from the carbon and showing the tetrahedral shape. But in either case, when you start visualizing the molecule in this way, you start to realize there's actually an infinite ways that these things can be configured. And that all comes from the notion that this is just a sigma bond right here. We learned that in the video on sp3 hybridization and sigma and pi bonds. This is just a sigma bond. Sigma bond. And so we can rotate around the bonds. One of these carbons could rotate around the axis of that bond without the other carbon having to necessarily rotate with it. If this was a double bond, if this was a pi bond, they would have to rotate together. So you could have a situation like I've drawn here, or you could have a situation where they're kind of rotated the inverse of each other. And this is what I mean. So I'll do a ball and stick. So let's say this is our front carbon, that is our back carbon, and we'll compare it to this one over here. So let me draw this guy the exact same way. So he's got a hydrogen down here. He's got a hydrogen down there. He's got a hydrogen up there. And then he's got a hydrogen up here. And then he's got a hydrogen up here. So that part of the ethane looks identical. Now what I'm going to do is I'm going to flip the other side of the ethane. And I want you to pay close attention because hopefully you'll see the difference between the two. So instead of doing this blue ethane down here, I'm going to do this blue hydrogen down here. I'm going to do it on top. So this blue one, I want to do that in blue. This blue hydrogen, put it on top. So I'm just rotating this around. So if the blue hydrogen's on top, so if I've rotated it, so the blue one's on top now, and now the green one is going to go over here. So now the green hydrogen is now over here, and then this purple or this magenta hydrogen, the way I've rotated, is now going to go over here, is now going to go over there. So what's the difference between this configuration and this configuration right here? And we could have had every other configuration in between, but what's the real difference here? Well, here the hydrogens are all, you can imagine that hydrogen is kind of, if you were looking from that direction, that hydrogen is directly behind that hydrogen, that hydrogen is directly behind that hydrogen, that hydrogen is directly behind that. This is called an eclipsed configuration or an eclipsed conformation. So eclipsed conformation. And this right here, nothing is behind anything. If you went straight back from this guy, you'd get to this point, and no one's behind it. And if you went straight forward from this guy, you'll get. So in no way are any of the guys in the back, if you're viewing from this direction, are they blocked by any of the people here? So we call this a staggered conformation. Staggered conformation. Now, why do we even care? Okay, I can twist around this this back molecule. What's that even going to do for our actual? Why does it even matter? Well, one, it's just interesting that you can actually change that this thing can twist around without changing the front, without the front molecule having to twist with it. But even more important, these have different energy levels. So you can kind of think of them as you're kind of twisting a spring, and the spring might want to go back to one conformation or another. And to visualize it a little better, I'll draw what's called a Newman projection. A Newman projection. So I'm going to draw this exact thing, but with a Newman projection, you draw the carbon molecules directly in front or directly behind each other. So in this situation, you would draw the carbon molecule in front would just be the intersection of these bonds. So for a Newman projection, let me draw that out. So it's a Newman projection. And I'll start with the Newman projection for the staggered conformation. So in the front, we'll consider this carbon the front carbon. We have our hydrogen pointing straight down. We have our hydrogen pointing straight down like that. And we have a hydrogen coming out to the top left like that. And then we have this hydrogen over here coming up to the right. I want to do that in that same color. So the front carbon is implicitly at the intersection of the bonds of these three hydrogen, and then the back carbon, I said the front carbon is the intersection of the bonds of these three hydrogens. The back carbon you represent it as a circle. So this circle represents the back carbon. The front carbon is kind of that point there. Just a way of visualizing it. But if we were to draw it this way, the back carbon now has that blue hydrogen popping off of it. So it has that blue hydrogen. So it would look like, so it has that blue hydrogen, this green hydrogen, that green hydrogen, and then this magenta hydrogen. And then you have this magenta hydrogen. And when you look at it like this, it is more clear that it's staggered. We're just looking straight on to this ethane molecule. And we look straight on the front carbon. They're obviously blocking each other. But this way you can see the front carbon's hydrogens are staggered relative to the back one. So this is right here. Once again, this is staggered. Now let's draw the eclipsed conformation as a Newman projection. So as a Newman projection, the front's going to look the same. You have a hydrogen. There, you have this hydrogen, you have that hydrogen, and then you have that blue, or I guess that purple hydrogen down here. So that's the front of it. But the back, they're right behind it. So let me draw the back carbon. Remember, the front carbon is kind of represented by just that dot. The back carbon will represent like that. Now, in the staggered conformation, if this guy is really behind that, you're going to have to draw it like right there, like right behind it. But since that's a little bit messy, normally when people draw a staggered projection, an eclipsed conformation as a Newman projection, instead of directly eclipsing that back hydrogen, they'll put it to the right a little, or they'll push it off a little bit. So that's that hydrogen. That magenta hydrogen is right there. It's really right behind the front one, but this is just so you can actually see it, that it's there. And then finally you have this blue one down there. So that blue one is going to be right over here. So this is the eclipsed conformation as a Newman projection. Eclipsed conformation. And as you can see, it's eclipsed. The back hydrogens are eclipsed by the front ones. If I were to draw it perfectly, they would be right behind it. Now, there's one other piece of, I guess, one more idea I want to introduce you to, and that's the notion of the angle between the different hydrogens. So if you wanted to say, well, what is this angle? What is this angle between the blue hydrogen and this pink hydrogen right here? Now, when you actually think of it in 3 dimensions, it's like, wow, you can't really say the angle over here between the blue and the pink. But when you on a Newman projection, when you're just saying how much are they rotated away from each other, this angle right here is called a dihedral angle. Dihedral angle. Sometimes it's just said, this hydrogen relative to that hydrogen has a dA of, in this case, 60 degrees. In this case, this hydrogen relative to that hydrogen has a dihedral angle of 0 degrees. And it's a way of saying how staggered or how eclipsed you are. Now, one last thing. I touched on the idea, like, why do we even care? Well, all of these hydrogens have electron clouds around them, and all of these bonds have electron clouds around them. And electron clouds, they're all negative, so they want to get as far away from each other as possible. And they're all stable now because they've bonded in ways that they have nice stable structures. Everyone feels like they have full valence shells, full orbitals. And so the electron clouds want to get away from each other. Now, in this situation, in the eclipsed conformation, this hydrogen and this hydrogen, this hydrogen and this hydrogen are closer to each other than when you go to the staggered conformation. The staggered conformation, the closest hydrogen to this guy is going to be either that hydrogen or that hydrogen, but they're both further away than this hydrogen was in the eclipsed conformation. So in general, the staggered conformation is going to be more stable. It's going to have a lower potential energy. You can imagine that if you start with an eclipsed conformation, these guys are all want to get away from each other. So it's kind of like this is the wound conformation. It has higher potential energy. So it'll want to unwind, and it'll want to unwind to a staggered conformation, because in this conformation, all of the hydrogens have gotten as far away from each other as they can get.